Today we're talking about Riemann sums. And if you look at the objective, it says we're finding an alternative to the trapezoidal rule for estimating a definite integral. So we're talking about definite integrals. So let's look down at number 1. This symbol, which I'm going to rewrite out here, this integrand, that's an integrand symbol, from a to b of our function f of x times dx stands for the definite integral of f of x from x is a to x is b, which means we're really looking for area. So in number 1, it's asking us to count squares to find an approximation for the area under the curve under f of x from 2 to 14. So I'm going to start at x is 2, I'm going to stop at x is 14, and I'm going to estimate the area under this curve by counting squares. Now, just to forewarn you, we're going to draw other things in this diagram of this graph in a little bit. So if you do write inside of the graph, you're going to want to eventually erase it. I'm going to go ahead and count up my squares. And when I counted up my full squares, I got 12 full squares, and then I pieced some together and I said, okay, it looks like these two maybe add to a single. That's maybe 13, that's maybe 14, and I thought that's a little more than 15, and I said 15 and a half. So that's how I added my squares up. So when I added my squares up, I got 15 and a half squares. But by looking at my scale of my x-axis and my y-axis, I know that's not actually the area under the curve. So each of my squares on my grid, across the bottom, I go across 2, and I go up on the y-axis 10, which means this area of each square is 20, which means if I want to estimate the definite integral from 2 to 14 of f of x dx, that's going to be 15 and a half times 20. And when we multiply 15 and a half times 20, I got 310. So this is my estimate for the area under the curve between x's 2 and x's 14. So right now I'm going to erase what I have on my graph to go ahead and do the next question. So moving on to number 2. Find an estimate of f of c. Okay, so what does that really mean? I'm finding an estimate for a y value for these x values. So all it's saying is when you look at the graph, when you look at x is 3, which again is an estimate, we're going to estimate what is that y value. So all I'm doing is look at the graph. That's all I'm doing. We're not counting anything, but using y values. When I look at 3, I'm going to estimate that is about 17. When I look at 5, I'm estimating that is about 12. When I look at 7, I'm estimating that to be about 15. That looks a pretty good 15. When I look at 9, I'm estimating that to be, I probably underestimated this one. No, I would say 26. 26. When I look at 11, 39. It's not quite at 40, I don't think. And at 13, I'm going to estimate that as 46. Now, you probably want to use my values for the remainder of what we're doing, just so that your answer and my answer are the same. If this was an assessment, I would not expect that your y values were my y values unless I provided a table for you. So all we've done is find our y values. So now it says we need to draw rectangles between the vertical grid lines with altitudes, altitudes, okay, that just means the height of the rectangle, equal to f of c. F of c is just the y value. So the height of the rectangle is going to be the y value, okay? Starting at x equals 2 and ending at x equals 14, tell y the sum of these of the areas is an estimate for the definite integral. So let's go ahead and start by drawing in our rectangles. So I know I'm going to start at 2 I know I'm going to end at 14, and I'm going to have rectangles. So when I look at the first one, when x is 3, y is 17, again, that's x, that's y. So I have a rectangle here, and it's telling me the height should be 17. So I really am looking to go kind of right in the middle of the x values between 2 and 4, and there is my rectangle. And again, my height was 17. Of course, my width I can see is 2. And knowing that, I should be able to find the area of that rectangle. Moving on to the next one, when I'm using the height of this rectangle is going to be 12. So here's 12 estimated. And again, this is 12 right here. And this is 2. Next rectangle, we are going from 6 to 8. And the height is going to be the y value, which is 15. So again, this is 15 right here, and this is 2. Next rectangle, I'm using the height of 26. So this is 26. That's a 2. And my width again is 2. My next rectangle is from 10 to 12. The height of that one is going to be 39. I didn't draw that very well. It should be 39 right below the 40. And again, my width is 2. Next rectangle is from 2 to 14, and its height is 46. And I have that drawn in. It's 46, and my width again is 2. So I've drawn in my rectangles. Just a minute, I'm going to scroll down. Drawn in my rectangles, and now I need to tell why the sum of the areas of these rectangles is an estimate of the definite integral. So if I were to find the area of each of these rectangles and add them up, what I would have is, when I look at this first rectangle, I have some area that I'm not including that's under my curve, but my rectangle doesn't count that. However, when you look right here, there's some area in my rectangle that is above my curve. And hopefully what happens is those two areas balance each other out. So what I'm missing and what I've added in that's not really part of my area under the curve should be close to equal. So let's look at another rectangle. So looking at this rectangle. This is part of the overestimate because it's outside of the curve, it's above the curve. And then this area right here, I didn't include in my rectangle, and so this is part of an underestimate. So hopefully those two balance each other out. So let's go ahead and write something down for number 3. So some rectangles, when we draw these in, only cover area that is under the curve. Other rectangles are going to cover area above and below the curve. And those are the ones we were talking about. Hopefully they balance each other out. And then still others, rectangles, cover more area than is just under the curve. So this should be a good estimate because we should balance out the overestimates and the underestimates. If you're not finished writing that down, pause your video now so that you can get that all copied down. Moving on to number 4. Number 4 says the sum of the areas of the rectangles mentioned in problem 3. That's called a midpoint Riemann sum. So the sum tells us we're going to add the rectangles up. I'm going to add the areas of the rectangles. The Riemann, this word Riemann right here means the shape we're using is rectangles. And then we have this word midpoint. The midpoint means that the height of the rectangle is the y value at the midpoint of the x interval. Now that may not make a lot of sense, but let's look at our graph. When we looked at our graph and we looked at the first one, this guy right here, we used when x was 3, if you come down to our table, we used when x was 3, we used the y value there. And that was the height of our rectangle. So that's how we got the height was 17. So that's what I mean by the midpoint Riemann sum. So I'm going to erase what I wrote. So if you need to write it down, you need to pause the video. Now, what we're going to do is actually estimate this sum. So let's add these areas up. So the first rectangle, the width is 2 and the height was 17, and that's 34. The next one, the width was 2 again, the height was 12, that's 24. The next one, the width was 2 and the height was 15, and that gives us 30. The next one, the width was 2 and the height was 26, and that gives us 52. The next one, the width was 2 and the height was 39, and that gives us 78. And the last one, the width was 2 and the height was 46, giving us 92. So if we add those numbers up, all those areas, 34 plus 24 plus 30 plus 52 plus 78 plus 92. So we add those all up. We're going to get our estimate. So the sum is 310. So the midpoint Riemann sum is 310. Again, it's still an estimate of the area under the curve, but it's probably a better estimate than, actually it's the same estimate we got when we did counting squares. But typically the rectangles are about as accurate as counting squares, and I think it's a lot easier. So for number 5, we're going to find some y values. And again, you're going to probably want to just use my y values. When x is 2, I estimated that to be 19. I'm going to erase my graph so that you can see on the graph a little bit better. That's where these came from, because I know your graph is really busy right now. When x is 4, I estimated that to be about 14. When x is 6, I estimated that to be about 12. When x is 8, I estimated that to be about 19 again. When x is 10, I got that estimate to be about 33. And when x is 12, I got that estimate to be 44. Now, if we look at our table, I'm going to scroll down a little bit. We look at our table that we had in number 2. And we look at the sums that we were doing in number 4. We were taking 2 every single time because that was the width of the rectangle. So that was the rectangle width. And we were multiplying it by the height, which was just a y value. So if we were to look at what we have here, that's exactly what we're going to do again. Now, if that doesn't make sense, draw yourself a little graph. And mine's going to be a terrible, terrible estimate. So I'm going to start at 2. I'm going to go to 4. And then I'm going to go to 6. And then 8. And then 10. And then 12. Now, the height for 2 is going to be at 19. So I'm going to write that down here. 19, and my width is 2. So I can find that area. Between 4 and 6, I'm going to use 14. So this is going to be 14 right here, and again our width is 2. The next one is 12. Why did I hit that bigger? I don't know. My green should be lower. 12 is here, so this should be 12, and again my width is 2. Between 8 and 10 we have 19, which should be the same height as the other red one. And then between 10 and 12 we should be at 33. And I forgot the last one, which was at 14, and that height should be 44. It should be above all of them. So if looking at a table doesn't help you, then go ahead and draw yourself a little graph, and then you can find the areas of all of these rectangles. So when I do this area, the first one is 2, the width of the rectangle, times 19. And again, looking at the table, it's just 2 times 19. That comes out to be 38. The next rectangle is going to be 2 times 14, which is 28. And again, there's the 14 right there. The next one is 2 times the height of 12, badly drawn rectangle, and that's 24. The next one is 2 times the height of 19, and that is 38 again. The next one is 2 times the height of 33, which is 66. And the last one is 2 times the height of 44, which is 88. And when you add this all up, this sum comes out to be 282. That's what I got. So what we're going to do now is compare how is this related to finding an estimate of an area by using the trapezoids. And basically, both are area estimates. So both are an estimate for area. The shapes are different. That's all. That's all we're really doing. So I do want to discuss the integral notation, and it's got an f of x dx. So when we had it written in blue over at the left, we had f of x times dx. And what that really means is from a to b, we're multiplying the height, which is the y value, times the width of the rectangle, which is your dx. That's all it really is. So that integral, definite integral from a to b of f of x dx is simply multiply the height times the width, and the integral actually just tells us to accumulate those, add those up. So moving on to the next page. All I want to do is I want you right now to draw a picture of each of these. So in number 1, you're just going to sketch a graph, whatever you want it to look like. Okay, and you don't need a lot of rectangles, but let's say you're going from A to B, and you're going to demonstrate what those rectangles would look like. Let's say 3 or 4 rectangles, and the width is going to be delta x, whatever that is, and the y value will be the midpoint within the delta x interval. And then you're going to do the same thing for the right Riemann sum. We're always going to use the right end of our rectangle as our height. And then for the left Riemann sum, we're going to use the left end for the height. So go ahead, pause the video and fill this all in. And then when you play the video again, my diagrams will be there. So here, in number 1 is my diagram of the midpoint. And typically the midpoint rectangle, the overestimate and the underestimate are pretty good at balancing each other out, as you can see in this diagram. Number 2, the right Riemann sum. I'm always pulling from, if I'm talking about this rectangle right here, the height is going to be the right side. If I'm talking about this rectangle right here, the height is coming from the right side. And it's not always an underestimate. In this particular curve, a right Riemann sum is an underestimate, but in a different curve, it would be an overestimate, or it could be great. Moving on to the left Riemann sum. So the left and the right are very similar, except that when we are looking at, let's say, the first rectangle, the height is from the left side of the interval. So in this rectangle, the height is again from the left side. So please make any corrections to your diagram, and I hope you have a wonderful evening.